We often like to think in black and white, yes or no, this or that. But most things in life aren't so simple. Take colors. Sure, we have black and white, but there's a whole spectrum of grays in between. The same goes for temperature. It's not just hot or cold. There are warm days, cool mornings, and everything in between. And pH, not just acid or base. There's a whole range of pH values. So when we talk about whether a reaction is or is not spontaneous, it's tempting to think of it as a strict yes or no. But just like color, temperature, and pH, spontaneity exists on a continuum. This is Real Chem. When we talked about the spontaneity of a reaction, we thought of it in terms of the change in free energy, delta G. Reactions that are uphill in free energy don't happen spontaneously, while reactions that are downhill do. But this isn't just a yes-no question. Reactions can be more or less spontaneous. And because the spontaneity of a reaction is such a crucial idea in chemistry, we actually have 3 different ways to describe it. Let's explore the many ways to describe the extent to which a reaction is or is not spontaneous. Imagine a spectrum. On the left, we have reactions that are very not spontaneous. On the right, we have reactions that are very spontaneous. Let's start by considering how delta G can be used to place reactions along this spectrum. On the far left, delta G is much greater than 0. These reactions are very uphill in free energy. They barely progress towards products and instead strongly favor reactants. On the far right, delta G is much less than 0. These reactions are strongly downhill in free energy. They go almost completely to products. In the middle, delta G is 0, meaning the reaction does not favor either reactants or products. Reactions can lie anywhere along this continuum. Some may have a small preference for reactants, and some may have a small preference for products. This preference is also described by the equilibrium constant K. For reactions that are very not spontaneous, K is much less than 1. The equilibrium lies far to the reactant side. For reactions that are very spontaneous, K is much greater than 1. The equilibrium lies far to the product side. And when delta G is 0, reactants and products are equally stable. That means K equals 1. There's an important difference in convention here. For delta G, the center of the scale is 0, but for K, it's 1. Now, let's bring in E0, the standard cell potential. This applies specifically to redox reactions. For redox reactions that are very not spontaneous, E0 is much less than 0. That means a strongly negative voltage. For redox reactions that are very spontaneous, E0 is much greater than 0. That means a strongly positive voltage. In the middle, when there is no preference for either reactants or products, E0 is 0. Note that delta G and E0 have opposite signs. A negative delta G means a positive E0. This makes sense. A reaction that is downhill in free energy can be used to generate electrical energy. So these 3 values all describe the same thing. They tell us how spontaneous a reaction is. But they don't just agree qualitatively, they contain the same quantitative information. If we know one, we can calculate the other 2. For instance, given delta G, we can calculate the equilibrium constant using this mathematical expression. We can also go the other way. Given K, we can calculate delta G. And similar expressions allow us to connect E0 to both delta G and K. That means delta G, K, and E0 are 3 different ways to answer the same question. How spontaneous is this reaction? So just like color isn't just black or white, and temperature isn't just hot or cold, spontaneity isn't just yes or no. Reactions exist on a continuum, from very not spontaneous to very spontaneous. And because this idea is so important in chemistry, we have 3 different ways to describe it: delta G, K, and E0. Each one tells the same story, but in a different language. By understanding these connections, we gain a powerful tool for predicting and controlling chemical reactions.